This talk is titled Simply RaTT, a Fitch-style model calculus for reactive programming without space leaks. And this is joint work with my supervisor Rasmus Møhleberg and our colleague Pratik Bar. So first off, what is a reactive program? A reactive program is a program that has continual interaction with the environment. This includes control software, server, graphic user interfaces, and so on. Traditionally, they are done in an imperative way where you have a shared state and callbacks. The problem is this is error-prone and it's difficult to reason about. And this is very important nowadays because many safety-critical systems are reactive systems. So we want to do better. So we want to do functional reactive programming. And why? Well, we want to reason about our reactive programs. We want high abstraction with efficient implementations. We want modular programs. And importantly, we want safety guarantees. We want to know that our programs do not go wrong. Functional reactive programming is programming with signals. And signals are these special kind of values that vary over time. And now our programs become signals transducers, right? You take a signal of A and you produce a signal of B. So one way to implement this is with signals as streams. So a stream is this data type where you can unfold it and then you get a head and then you get a tail, which is another stream, right? And then you can keep unfolding. And in the functional reactive setting, we somehow think of this as taking time, right? You get the head now and you get the tail later. If you implement FRP with signals as streams, there's a known problem, and these include causality, productivity, and space leaks. Causality. We say that a program is causal, or you could say implementable, if the nth output depends only on the first n inputs. Okay, so here's a program that's not causal. So we take a stream of A, then we output the head of the tail of the stream, and then we keep doing that recursively. And this is not causal because the first input depends on the first output, depends on the second input. So this is non-causal. We say that a program is productive, or you could say useful, if something is output at every n. So here's a non-productive thing, and what is it? Well, it's the tail of itself. So this doesn't do anything. You can write it and then it runs forever, it doesn't do anything. The property of a space leak is slightly more complicated, but you can say that a program has a space leak if the execution of the program uses more memory than expected and the memory is released later than expected. Okay, so here is, let's look at a program, right? So here's a program, it takes two inputs, it takes a Boolean stream, right? So false, 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 true, and so on, and it takes a natural number stream. And the function we want to implement, or the program we want to implement, is a program that every time the Boolean stream is false, it outputs 0, and every time the Boolean stream is true, it outputs the head of the natural number stream. Okay, so notice the head is outputted both times, so it only ever is 0 or in 1. Okay, so one way to implement this is as follows, right? You take the stream of Booleans, you take the stream of natural number, and we produce a stream of natural number. And then we use this internal function that says, well, we take a Boolean stream. If the head is true, then you output the head of the natural number stream, and you continue. Otherwise, you output 0. And then we do this on the Boolean stream. And the problem here is that until we actually get true, we don't know really what to do with the natural number stream, right? So we just have to keep this thing around. We keep buffering this thing. And unless you have some extremely eager evaluation strategy, you will have to keep the stream around, right? And possibly forever, because you might never get a true. So this will lead to a space leak, right? You will have to retain the full natural number stream. The problem here is that streams are not stable over time, and this can lead to these kind of leaks. So what you can do instead, well, is you can say, well, as a programmer, we know that we will only ever use the head, so we just take the head up front of the natural number stream, then we do the same thing, except instead of doing the head call inside the if then else, then you just put in, right? And this is fine. So now you run your program, the stream is garbage collected and it goes away, and you only retain this natural number, so that's fine. So the idea here is that to avoid leaks, we should only store stable values, right? We should only keep these stable things around. But the problem is they cannot really be differentiated in this naive approach. So we want to do something else. One possible solution is that you simply restrict the API. You say, well, you don't have direct access to signals because this can lead to these kind of leaks. So we restrict FRP to predefined combinators, right? So you don't have direct access, you just have some combinators on hand. And this can be very successful, right? This is the errorized FRP approach where arrows are signals transformers, then you get a bunch of these in hand, and you build a program of these, and then we hope that somehow these predefined combinators are leak-free, right? The problem is that you lose the simplicity in the you lose the simplicity and the flexibility of the original formulation, right? We really want to have first-class signals. So what can we do instead? Well, one solution is to do modal FRP, and this has first-class signals. So modal FRP is FRP where we add modal types. And in particular, we add this modality, which I denote by this triangle, which is pronounced later or delay. And the idea is that later A represents A one time step from now. So in the next time step, you get an A. And now we work with guarded streams. So notice here now the unfolding of the stream, you get the head of A still immediately, but now the typing really says you get this tail later, right? You only get the tail in the next time step. And this immediately fixes causality. So the program from before, this non-causal program, this will be rejected by the type checker now. And why? Well, because the tail of AS is now a guarded stream, right? So it's guarded by the modality, and then you cannot call head on it, right? You cannot call head on a stream in the future. So this will just be rejected by the type checker. And you have similar for productivity. Okay, so let's look at what we have done here. So the goal of this research is to create a full dependent type theory for reactive programming. This is what we call RaTT, reactive type theory. So far we have Simply RaTT. Simply RaTT is a simply typed calculus for Modal FRP, and this uses a Fitch-style approach. I'll return to what this means precisely, but this removes the need for let bindings, and it allows for simple and concise programs, at least we think so. And what we have is a heap-based operational semantics for streams and stream transducers. We disallow implicit space leak by construction, and this is a result following Krishnaswamy for a similar language. And we have a type system that ensures safety, causality, and productivity. So let's see what it looked like. So in a streaming sense, the simplest you can do really is create the constant stream over some element, right? So the stream that is just the same element in each time step. And immediately we see this. To do this, we have to get a stable thing, right? We have to get something stable in hand to repeat it many times in the future. So the way to read this function declaration is that we have this token, and this is called a lock. And the lock separates the content into the dynamic things. You can say things where time somehow plays an important role, and the non-dynamic things. So things you have just non-dynamically. And this will become clear, hopefully, as we move on. So what do you do? Well, you get something non-dynamically, right? You have this element in hand before you even start thinking about the stream, and then you can create a stream. And what do you do? Well, you use A immediately as the head. Now we want to delay, right? So delay is the introduction form for the delay modality or the later modality. And this we don't want to do, right? Because remember, these are guarded streams now. So we say you get the A front, and then you get something in the next time step. And what do you do in the next time step? Where you recurse, you just do const again. And we know this is safe, right? Because A is a stable thing. We knew A is stable, so it's safe to do in the future. It's safe to push into the future. So what do I mean by dynamic behavior, right? So let's look at the zip function. The zip should take two streams and then pair up the element. And here, these two things are fully dynamic things, right? These are stream that unfolds over time. So these happen after the lock, right? So this is not given up front. This is somehow dynamic behavior happening dynamically. Okay, but given these two streams, what do you do? Well, you can pair up the heads immediately, so you get the head of the output stream. And now, again, we want to delay because we want to end up with a guarded stream, and then we want to recurse, right? But now something special happens. So we remember that the two tails are delayed things, right? They happen in the next time step. But now we delayed, right? So we should really be in the next time step. So it should be safe to use the tails. And this is what the advanced construction gives us. It says that, well, if you have delayed data and you move into the next time step, then you are allowed to use it. So this is what delays gives us. So we zip and we do advance. And just to show that we can have like fully dynamic behavior where we modify the flow graph, data flow graph, then we have this function. So this says, well, you get a stream up front, then you have an event that will trigger and give you a stream maybe, and then you should output a stream. And what do you do? Well, if you're still waiting for this event to trigger, then you just continue as the stream you have in hand. And again, you have to do this delay advance construction. And if you get the stream, then you just continue at that. Okay, so let's look at the type system. So traditionally, when you do Modal FRP, you use a dual context approach. So let's look at the introduction rule down here. In this approach, you really have two separate contexts. In one of them, you think of the now variables, so everything you actually have in hand now, and the other one you think as later variables, that is variables representing data that arrives in the next time step. And the way you can introduce from such a context is that you can only introduce from the now part of it, right? So you can only introduce variables you actually have in hand. Okay, so what do you do if you get something of a delayed type? You do a let binding. So you say this t is of later a, then you bind it to a variable x. This x is added to the later context, right? So now this x represents data that arrives in the next time step. And then you type t prime as type c, and then the whole thing is type c. And the point here is that if you had a fully dependent system and C were really to depend on X, then C itself will have to be some kind of let binding. And we don't really want that. So this is one of the motivations why we want to move away from this approach. And how do you create something of a delayed type? Well, to create a t of type later a, you throw away all your now variables, you think of your later variables as being now variables, and you have no further later variables, right? So you only think about one time step at a time. So there's nothing in the later setting, right? Then using only your later variables as now variables, if you can type t as a, then delay t has type later a. Okay, so what do we do instead? In the Fitch-style approach, we only have one context, but instead the context has tokens. So this token is called tick, or it's pronounced tick, and this represents, this can be thought of as a witness that time has passed. Okay, so if there's no tick there, all the variables are now. If you add a tick, we think of the variables as happening before the tick, so earlier. So note here there's a conceptual shift of how time happens, right? So before it was now later, and now it's now earlier. Okay, so how do you create something of a delayed type? Well, you still use this delay construction, and what do you do? Well, you add a witness that time has passed, and then you should be able to type t as having type a, right? So after time passes, t should have time a. If that is true, then it has later a before the tick. Okay, so what can you do if you have something of a delayed type in hand? Well, after time passes, then you can use it, right? So you can introduce it in the next time step. And the point here is now you really have to respect the token, right? So you cannot introduce variables across the time step, right? Because this would mean pushing arbitrary data into the future, and we do not want that, right? So you really have to respect the token. You cannot introduce a variable across the token. So we had this notion of stability also. So we need to know what variables we actually can safely transport into the future. And there's two notions here. One is things that are inherently stable. So these are natural numbers, units, products, and some of these. And the point is that these things never change, right? A unit is always a unit, no matter in what time step you use it. You can always introduce the unit. The second notion is given by the box modality. So given a type A, we want to restrict it down to all the stable terms inside that type. And this is represented by the box modality. And the point is that box of A is a stable type, no matter what A is. And this here we also use the Fitch-style approach, and this is where the log token showed up. So this is another token, and this is log, right? And the token here really separates the context into non-dynamic and dynamic things. So the way to read this typing rule is saying that, well, if you have some t of A, which you can use in any dynamic setting, right? So here you're allowed to do dynamic things, and you don't know when in time this actually happens. If you have a t of A that can function in any such context, then you're allowed to box it, and you get something of box A. And the point here is that, well, if you have something of box A, then you can introduce it in any dynamic setting. And in particular here, tick can happen in here, right? You can have a setting where you move back and forth in time, but you can always unbox t. So there might be a tick here, and you can actually still unbox it, right? So this can happen in any setting, in any future, so to speak. Okay, so to ensure causality and productivity of our recursion definitions, we use a modified Nakano-style fixed point. And the modification happens with the token here, and that is a box type. So normally, a Nakano-style fixed point just says if you have gamma and you want to do a fixed point, then you add a variable of type later A, and then you need to type A, and then the whole thing of type A. So instead, we say, well, that doesn't really hold in the functional reactive setting. And why? Because we really think of fixed point as unfolding in the future, right? We saw in the earlier examples, you really call these fixed points in the future. So they better be stable, otherwise you cannot use them, right? So it has to be a box type. And for it to be a box type, we have to add this log, right? So this is really, has a built-in boxing structure, right? And the point is, again, as it says here, they have to be stable, so we can use them in the future, right? And the idea is that in general, we do not have a function A to later A, because this would allow us to push arbitrary data into the future, but we do have box A to later box A, right? So if it's a box A, i.e. it's stable, then we can push it into the future. And this needs to be the case for the fixed point. Okay, so let's look at some examples in the actual language. So first of all, these tokens have nice behavior. They are both applicatives, right? So if you have a later A, if you have a later A to B and a later A, you can get a later B. And what do? Well, you delay, then you advance 2 times and you apply the function. And similar, the box has an applicative structure, right? You have a box A to B and a box A, you get a box of B. And what do? Well, you box and you unbox appropriately. Okay, so let's look at an actual function in the language. So this is a mapping function. So this takes a map of A to B and a stream of A, and it produces a stream of B, right? But this is not good enough in the functional reactive setting. So what needs to happen? Well, it needs to be a box function. And why? Well, because we want to apply this function many times. So we want to apply it at every time step in the future. So it better be stable. Otherwise, we can't do that. And what do you get out? Well, you get a stable thing out, right? So you get this stream of A, meaning that the new mapping function you created can be applied at any time in the future. Okay, so what do? Well, we get the box thing up front, then we do a fixed point, and we want to do a fix of map, then we get the stream, then we want to apply the F to the head of A, and to do that we have to unbox it, right? So now we pull the F inside the map, and to do that we unbox it, and we apply to head, and then we do that recursively, right? And here we use the applicative structure, right? So here we say we delay, we do the recursive call, and we apply to the tail, which is then advanced, okay? And to represent this in our simplified syntax, well, the log here now really represents splitting before and after the fixed point happens, right? So the stream here happens dynamically, and the F is given
so let's
up
move
front,
on
right?
to
So
semantics.
the stable thing is given
so
up front,
we
and the
define
dynamic
2
things is given
heap-based
after.
semantics for
And
SimplyRaTT,
basically
liberation
we do the same.
semantics, and a step
Okay.
semantics. And the step semantics is used for unfolding streams over time. And really, we kind of define 3 semantics because we have to modify this a bit to do transducers, but we'll see that as it comes along. So the evaluation semantics describes how a term evaluates to a value with a given store. And I'll return to the store shortly, right? So you take a term and you evaluate it to a value. The step semantics describe how a stream evaluates over time, right? So in each time step, we can do an unfolding, and this describes how that works. So given some box stream of A, meaning a fully defined type, we have this sequence. Well, you unbox it to get a stream of A, and then you can keep unfolding it. And each time you emit a value, and this value is the head of the stream at the current time step. Okay, so what about the store? In both cases, the store is used for delayed computations, recursive calls, and importantly, it's used for input data for transducers. So we'll see this in a second. Okay, so the store is of this form. There's 3 possible cases. Either it's this special thing called a null store, it's a single heap, or it's 2 heaps separated by a tick. And in both cases, heaps are finite maps from location to terms. And the shape of the store corresponds directly to capabilities, because this really describes a kind of storage effect. So if you evaluate in the null store, it means you can neither read or write, right? There's no data retention, and there's nothing you can do. You can neither read or write. If you have a single heap, this allows writing but not reading, because the idea is that this allows you to write data in form of delayed computations, but you can't read anything. If you have a tick, then you have delayed computations from the previous time step, so you can read those, and of course you can allocate for the next time step again, right? So here, the now heap here, we call these now and later heaps. So the now heap here describes whatever data was delayed in the last computation step. And again, here, both here and here, this describes data I allocate for the next computation step. Okay, so let's see what actually happens in these rules. So let's look at delay and advance. So delay first. So if we have a term delay t, we need to be in a store where we can allocate data, right? We can write data. So this means the store cannot be the null store, but it can either be a single heap or a ticked heap. So what do? We allocate a new label, and here we assume we have a deterministic allocation function. So we allocate a fresh label, then we return that label, and we extend the store with this new term t. And the extension, this is just a shorthand, meaning that you always extend on the later heap, right? So now I allocate some data for retrieval in the next time step. So what happens when I can actually read some data? Well, then I can do this advanced construction. So if I have a heap, and here the heap has to be a ticked heap, or the store has to be a ticked store, right? Because there should be some data available that I can read. So what do? Well, first of all, we evaluate this t, because this needs to be a label before we can read it. And here, this is some kind of lazy evaluation, right? Because here, maybe the term was not actually allocated on the store yet. So conceptually, this happens in the past, right? You remove the tick, so you go back to only having the now heap. Then I make sure what I want to read is actually allocated on the heap. So it might be a label already, but otherwise you allocate it now. Then I look up my allocation, and I do this in the full store, right? So I go back, so now I'm in the store again where the tick is available, and this should evaluate to some term. Okay, so this is reading from the store. So what about the null store? Well, the null store really describes when you do a non-dynamic evaluation, right? So if I want to unbox a term, I can do this in any store that's not the null store. But this T here, well, this should really be something stable, right? This should be something proper non-dynamic. So what do? Well, we evaluate it by in a store where you can neither read nor write. There's no dynamic behavior here. This should evaluate to a box of some term, right? And then that term is allowed to evaluate in any store as long as it's not the null store, right? So this is allowed to evaluate in an environment where there's reading and writing going on. And so note here, there might already be some stuff allocated, there might be new allocations ready, old data and so on, but this store should be able to just work there. And this is enforced by it being evaluated by neither reading or writing. And the same thing goes for the fixed point, right? Remember, the fixed point is a box type, so we also need to unbox it. And the idea is the same, right? The fixed point should be evaluated in an environment where you can neither read nor write. And then here we do an unfolding of the fixed point, and this is slightly complicated because we have this slightly non-standard type, but really this is just unfolding of a fixed point, right? And then you just put in these box delays and unbox to make sure the types match up. But the idea is the same. You evaluate it to a fixed point in an environment where you can neither read nor write, and then you can actually use it in an environment where you can either write or both read and write. Okay, so the step semantics. The step semantics describe how a stream unfolds over time. Okay, so assume we have some term of type stream of A, and we have some store. Well, a store, so there might be some allocations already there for what happens in the next time step. Then what do? Well, then we step time, so to speak. So we say we add a tick. Then the term evaluates. Since it's a stream, it evaluates to a head, which you get available now, and a tail. And the tail is a delayed stream, right? Meaning it's something that is allocated in the future. So here, this label lives in the later heap, okay? And then we say the whole term steps, it admits the V, which was the current head. And then in the next time step, we remove the now heap, and then we can advance this thing and it lives in the later heap. And then we can keep doing this, right? And the point here is that after evaluation, we delete the entire now heap, right? So note this, from here to here, we delete the now heap. This includes whatever was already allocated. So whatever data was already given and whatever data was created in the now heap during evaluation is removed. What this means is that all data must be explicitly moved forward to remain available. Okay, so if you want data to be retained across these steps, it must either be in the form of something delayed or some stability construction, but either way you have to explicitly move it forward in time because otherwise it's deleted. And this is what we mean by removing implicit time leaks, implicit space leaks. Data is not retained unless you explicitly do it. For the transducers, we also have a step semantic, and this is a little bit more complicated, and that's because we have to handle input data. Okay, so let's go through it slowly. So again, if we have some T here, and T is now type stream A to stream B. We have some EDA, meaning already allocated data, and we have a label now. So the label is a new element. It's a new thing in this semantics. And what the label does, it points to where the input data is available. Okay, so the input data to this thing should really be a stream of A's, and then I need to produce a stream of B's. And the L points to where the input data is available in the current time step. Okay, so I take my T, I evaluate it, and I evaluate in this store where I have the EDA, whatever was already available, or already allocated. Then I have this label, which I already chose. It points to V, which is the current input, so the current head of the input stream. And then it points to L prime. And L prime denotes the tail of the input stream. So this is data that's not available yet, but we need to allocate it. So we do an allocation, and then we just point it to a unit. And this is, say, well, the tail is here. It's not available yet. We don't know what the data is, but we need to allocate it already. So this evaluates, and again, it evaluates to a stream of B. So you get a head now, which is what we emit down here, and we get a tail. And importantly, the tail, again, lives in the later heap. And note the L prime allocation is still available. And then we say the whole term steps, we input V, we emit V prime. We can advance in the label in the next time step. And L prime is where the next data should live, right? So this is where you should put the next input data you get available. Okay? So the whole term steps, and we emit a V and we eat a V prime. And importantly here is the input data for the transducer is deleted after each evaluation, right? So in every time step, the input data is allocated on the now heap, and just as with the normal stream semantics, the step semantics, we delete the now heap, right? So you only have this data available in the current time step. It's removed in the next time step. So in each time step, we remove the input data. So it's not buffered unless you explicitly do some construction, which is not always available, right? But you have to explicitly move data forward if you want it to be available. Okay, so the main results we have in our paper, or the main result of this work, is two theorems, so productivity and a causality theorem, talking about the stream semantics and the transducer semantic. So productivity basically says, well, if you have some stream in hand, like a fully computed, fully defined stream, so a box A, then for any natural number, there exists a reduction sequence, right? So you unbox this, you have a stream of A, and then you can keep doing this reduction I showed you before, and you admit values. All of these values are of type A, and you can do this for any n, right? So for any n, you get such a reduction. The second result is a causality result talking about transducers, and this is slightly simplified from the actual result. That's just because there's some technical details. But in essence, what we prove is that giving a transducer and some inputs, there exists such a reduction here, right? So you unbox it again, so you get a stream of A to a stream of B, and then you can keep doing this transducer reduction. You input a V, you output a V prime, and you keep going. And all of these outputs are then of type B. Okay, to prove these results, we use a step index cryptological relation. So let's look at that. So first of all, let's look at what the worlds are for this crypto relation. So the worlds are triples, where sigma is a store, eta bar is an infinite sequence of heaps, and alpha is an ordinal less than omega. So the store describes the state of the store. The sequence describes possible future inputs, right? So these are a sequence of heaps, and each of the heaps describe whatever the input will be in that time step. And the ordinal is a step index. And as normal, there's an ordering of these worlds, and the ordering essentially says, well, you have less time to evaluate, and you extend the store somehow. It's all in the paper, but that's essentially what it does. Okay, so let's look at the semantics of delay. So what is the values of delay? So these are all labels, okay? So everything that lives in here is a label somehow. And then we take a world, and note here that the world, this is just, we just need to talk about the head. So all the input sequence looks like this. Okay, so if we have no time left to compute, well, then these are just the labels that live on the heap. And I will turn shortly to what this GC is. Otherwise, it's labels that I can advance, and then I can evaluate them in the next time step. So this is the term interpretation. The term interpretation just means it evaluates, and then you get a new value out. So these are labels that can evaluate, and you evaluate in the next time step, and we can see this in two ways. One, we step down on the index, right? So we have one time step less to compute, and then we do this shift here. And the shift here says, well, the garbage collection, this is where the safety result is semantically. So garbage collection says, if there's previous data allocated, you delete it, right? So otherwise you don't do anything, but if there were previously allocated data, you delete it. So this says we delete all the previously allocated data, then we tick, and then we add the next input data. So remember, the heap sequence describes input data. So delete the old data, tick, add the new data. Then you should evaluate there. So that's the idea of the delay. So the idea of box describes stability, right? So you say, well, the values here are all the terms that can evaluate in a certain setting, and the setting here says that, well, you can choose any input sequence, and you start from the empty store. And a note, importantly, the empty store is not the null store, right? The empty store is just the store where nothing is allocated yet. But because of the crypto properties, and in particular weakening, this really means you can go to any store you want, right? So the stable terms, or the box terms, are all the terms that can be unboxed and then evaluated in any input with any future inputs and with any current store state, right? So these really are stable. These are all the things that do not in any fashion use dynamic behavior. They don't read from the store, they don't allocate on the store, and they don't use any knowledge about future input. And the same thing holds for all the stable types, so the inherently stable things, right? So we have a lemma saying, well, basically a property reminiscent of this holds for the unit natural number, so forth. You can evaluate them in any store and with any heap sequence. Okay, so let's look at the context. So corresponding to the modalities, we have tokens, right? And so the tick describes the passage of time, right? So if you have a store if you have a context that has been ticked, well, really you do the reverse of what we did when we did the later, right? So if a ticked context looks like this, well, that means that the context before it must have looked like this, right? And note, we shift around here. The now store becomes the new later store, and the later store here becomes the next future input, right? So it really is the reverse of the later construction. And similarly, the log describes when the store is available, right? So this is really the reverse of the stability. It says, well, terms that live in the log store, like all the values that live before the log, must be non-dynamic values, right? So this would be values that don't have the store available at all and can handle any future input, right? So these are proper non-dynamic things that lives here. Okay, so let's look at ongoing work. And ongoing work at the moment is providing denotational semantics for Simply RaTT. And we really have two reasons for one. It's a step towards having a dependent type theory, which is really the goal of this research, right? We want to have the full RaTT system. And secondly, we want to understand Simply RaTT better way, right? We want to understand what actually goes on, like in a rigorous mathematical categorical sense. So what we want to do is we want to give a pre-sheaf model of Simply RaTT. And we use the same worlds as we do in the logical relations. So we have a triple where we have okay, let's leave fixed then. Okay, so let's move on to ongoing work. And ongoing work is providing denotational semantics for Simply RaTT. And we run this for two reasons. So first off, we're really aiming to doing a dependent type theory, right? We want the full RaTT system, and this is a step towards that. And secondly, we want to understand better what we're actually doing here in Simply RaTT. We want to have a proper categorical understanding of what's going on. So we're trying to build a pre-sheaf model for Simply RaTT. We are using the same worlds as we did in the logical relation. So we have a triple of a store, a heap sequence, and a step index. And in this system, the modalities and the tokens are interpreted using adjunctions, right? So we have these kind of isomorphisms in our category. And this is a known approach to doing modal type theory, right? We want to have these kind of adjunctions. So we're saying that we really want that maps out of a tick context should really correspond to maps into a delayed type. And similarly, maps out of a log context should really correspond to maps into a box type. And secondly, the safety guarantee now is encoded using a garbage collection modality, right? So we define this modality. We say the garbage collection on A is really just garbage collection on the world, right? So this is precisely the same garbage collection that showed up in the Kripke setting. Okay, with this we say that types, or we prove that types are garbage collection algebras, right? So the types are the things where you have this kind of isomorphism, right? We say that a type should be isomorphic to the garbage collection of that type. On the other hand, terms are interpreted with respect to an appropriate store object, right? So these are not garbage collection algebra. Something actually happens when you garbage collect here. And in particular, we interpret a term as a type, a term of a type A as a map from this store object into the value interpretation of the type. And this store object is essentially just the interpretation of the heap, right? So it is some kind of iterated product over whatever lives in the heap in an appropriate way. And this really defines a kind of reader monad. So the terms define a monad somehow, right? And then the delayed types are interpreted using this monad, right? So the storage effect does really show up as a monad in this setting. Okay, so let me quickly sum up what we have talked about here. So what do we have? We have a Fitch-style approach to Modal FRP. We have a heap-based operational semantics that rule out space leak by construction. We have a type system that ensures safety, causality, and productivity. We have an idea of ruling out some time leak. So time leak is a different problem that happens in FRP. And this really happens when you have to recompute values too many times. And we have a heuristic for ruling these out, but I haven't talked about it because I'm not if you care about it, look up the paper, but otherwise this is just a bonus thing. And the meta theory has actually been formalized in COG. So the logical relation I talked about earlier has been formalized in COG. And the future work is that, first of all, it would be interesting to add many ticks and many heaps. So in the system so far, you only have a single tick, right? Just think about one time step at a time. But there shouldn't really be a problem going to many ticks and many heaps, meaning that you can think about multiple time ticks at a time. But so far it hasn't worked, and there are some interesting problems, but inherently it shouldn't be impossible. Then, as I said, at the moment I'm doing denotational semantics, and we really want this to go through. Then we want to build alternative. We want a logic on the language, and as I said at the beginning, we really want to extend to dependent types. But this is future work. So thank you for your attention.